Welcome to BDC's first birthday. My name is James Rowland-Jones, although many of you know me as JRJ, and I am the Group Program Manager responsible for BDC. You'll be able to find me on LinkedIn or Twitter, and I'm more than happy to talk to anybody about the New England Patriots, Arsenal Football Club, or even a little bit about BDC. Past Summit 2020 represents BDC's first birthday. It's hard to believe that BDC is already 1 year old. And I can't believe that we have been able to do quite so much in such a difficult time for so many people. But we have had our own ups and downs as we've gone through the year, and we want to take you through some of that in our session today. We've also going to talk about some of the things that we plan to do in the future. And so if you're interested in a few sneak peeks into what's coming up, then do please stay tuned and be able to see what's going on. But this isn't going to be an ordinary kind of BDC product group session where we'll talk about the architecture and this and the other. This is a community conference, and there's a lot of excellent speakers already here to talk to you about everything that they've learned in their first year with BDC. So what we're going to do with the BDC product group team and with everyone's support is actually talk about what I consider to be quite interesting capabilities of BDC. Things that you may not have had a chance to look at yet or have not really appreciated that are actually part of BDC. We all know about things like data virtualization, but we don't know necessarily about all the different use cases that we could use it for. We also all know about things like Spark and data science. But what about Spark at scale? What about how we can use notebooks to write new types of applications? That's what this session's about. We're going to show you lots of different things that you can do with BDC that maybe you hadn't thought about before. Now before we move on, it's important to remember that PASS is a community conference. It's here to support its members and the broader SQL community at large. And I hope that you take advantage of all of the capabilities and offerings that PASS brings to the community throughout the year, especially your local SQL Saturdays, where people give up so much time to enable you to continue your education experience and being able to connect, share and learn. And with that said, let's get on and start having a look at our first scenario. Availability groups is a high availability feature of SQL Server that's been with us for a while now. They enable you to create a single unit of availability across your user databases. However, there are a couple of challenges when using them. Firstly, there's a fair amount of manual setup. And secondly, that there are certain objects that sit outside of the database that are still part of your solution that can't fit inside an availability group. The key difference with a contained AG is that those objects, typically logins and database jobs from master and MSDB, can now be included in your availability group. So what we're going to look at now is how both BDC simplifies the creation and management of your availability group, but also what exactly goes inside it, which includes your master and MSDB databases. Let's have a look. For this demonstration of contained availability groups, we're going to be using Azure Red Hat OpenShift as our Kubernetes environment. BDC introduced support for OpenShift and ARO in CU5 earlier this year. Now, when it comes to Kubernetes, BDC targets a namespace. In OpenShift, a namespace has been formalized into something called a project, and so that's where we will start our exploration. Our instance is called MS SQL BDC, and so we can search for it and find it right here. The cluster we're using is one of our development clusters, so there's lots of projects that have already been deployed into this cluster. From this project, you can see all of the resources that we have deployed as part of the BDC instance, including the services which expose the external and internal endpoints to the cluster. So let's go ahead and click on the services link so that we can locate the master pool. And you will see that there are 4 instances. But we're only interested in the external endpoints, so we apply a further filter. Here we can see the primary and the secondary endpoint so that you can access the readable secondaries as well as the read-write primary. If we click on the primary, we can also see the IP address of that load balancer as well as the port which has been exposed. And by clicking on the pods, we can see which pod is in fact the primary, and in this case it is master 0. If we go back and look at the secondary endpoint, we can see a different IP address and a different port, as well as the 2 other pods that make up this contained AG. One of the things that you may not know about BDC is that SQL Server Agent is disabled by default. So we're going to have to enable it in order for our contained AG experience to work for MSDB. Now, we could have done this with an MS SQL conf file. However, we're going to show you a sneak peek into a new experience that we have coming for BDC early next year for configuration management. To use it, all you'll need to do is to log into AZ Data to access the controller, providing your namespace, username and password, and then you'll be able to use the new BDC settings configuration to be able to apply one or more settings to BDC. This will follow the Kubernetes pattern of set, diff, and apply. So you'll be able to set multiple settings, diff them against the controller to see which ones you have changed, and then apply, and all of them will be applied in a single upgrade. The upgrade experience for BDC for configuration performs a rolling upgrade, especially for the master pool, where it's incredibly important to do the secondaries first before touching the primary. We'll wrap this segment up with a quick BDC status show to prove that the cluster is healthy once the upgrade is complete. Let's briefly review our contained AG topology from inside Management Studio. If we click on the Always On High Availability folder, we can see our availability group and our contained AG. Drilling in, we can see the replicas and notice that master 1 is now the primary, as we rolled over the pods when we enabled SQL Server Agent. Now as we come down and look at the databases, we can see the contained AG for master and MSDB. Notice that they were automatically included as part of the contained AG. There was no additional setup required. Finally, here is the contained AG listener. We're going to come back to that later when we review secondaries. Now let's go ahead and create some artifacts into master and MSDB. The first thing we're going to do is to create a login and a database which will add to the contained AG. So let's go ahead and execute that now. Now it will take a little bit longer to create the database in the contained AG because it's automatically being added, and we'll see that in a second. We will also notice that the database is entered in a full recovery model because it is part of the contained AG, and we can see it now here is automatically been included. There were no additional steps that we needed to perform. With our login and database in place, let's go and create some objects in MSDB. So the first thing that we're going to do is to create a user for our login and assign permissions. Then we're going to create a database backup job and test it. So there we have the job created. We can find that in SQL Server Agent, refresh. Here's our job. We can now test that by executing it, and the job has run successfully. Now let's complete the scenario by adding some objects to our user database. As you can see over here, we are going to create a new user for our login and assign permissions, as well as creating a new players table and inserting the latest Arsenal player Thomas Partey to the players table. Lastly, we'll run a query and welcome Thomas to the party. Awesome. We can also confirm the primary is master1. We can simulate a failover of the primary by deleting the pod that is associated to it. In this case, we can see that master1 is the primary, so we can come over in arrow and simply complete the action to delete the pod. This will initiate the failover. Now, one of the big benefits of running contained AGs is that your logins and your jobs are moving with you because they're contained inside the availability group. So now, with that failover having taken place, let's go and connect with our new login to the database primary. And here we go. Automatically connected, no manual movement or recreation of logins and mapping those across all of the various pods. It's all been done for you by the contained availability group. Furthermore, my T-SQL agent job to back up the Arsenal database is also working seamlessly. So if this was on a schedule, I wouldn't need to worry about recreating the job on all of the pods and instances. Everything has been contained with the database. So with that in mind, that concludes everything that we need to talk about on the primary endpoint. Let's go and look at the secondary and see how those operate. So here we are back in Arrow, looking at the external endpoint for the secondaries. You can see by clicking on the pods which ones are in fact the secondary pods, readable secondaries. In this case, it's master 0 and master 1. Coming back into the details, we can scroll down and locate the IP address and the port for that endpoint connection, which we've made below. Now, the difference here between how load balancing works on the readable secondaries in Kubernetes on BDC is that we're actually taking advantage of the Kubernetes load balancer rather than using the listener for this purpose. So what you can see is if I make a connection and a query here, you can see that master 1 has picked up this one, and it will always be that way for that one session. However, as I add sessions and run them, you will see that it's up to Kubernetes which one picks up the instance. And you can see here that number 3 was the session here 3 had master 0. So you can see it is not strictly speaking any kind of round robining. You can see we went 1, 1, 0, 1. But it is up to Kubernetes to manage the load and do that for us. And that's one of the advantages of using Kubernetes, is that it does come with these additional capabilities. Well, that about wraps it up for our tour around contained AGs, our introduction to Thomas Partey, and our sneak peek into configuration management. I hope you're beginning to see that BDC offers you a unique experience when using SQL Server and introduces you to new capabilities. I hope you look forward to trying them as well. If you get feedback, don't forget to share it with us using the link above. Let's move on to the next demo. So now we're going to move on to data virtualization. Many of you, I'm sure, if not all of you, have heard about SQL Server 2019 data virtualization capabilities. But how many of you have thought about data virtualization in the context of Spark and also in the context of BDC, where we bring together SQL Server and Spark and enable you to use their unique capabilities to your best advantage? We're going to explore that in this next set of demos. With this notebook, we're going to be doing some data virtualization and data movement using nothing but T-SQL. As you can see, I've already created a database for us to use in SQL Server. It's called TPCDS1TB because we're going to be using the 1 terabyte scale factor of the TPCDS dataset as our data source, and that data is already resident in the storage pool of BDC. So to get started, the first thing we need to do is set the execution context for the notebook. This ensures that everything that we do with the notebook from here on in is going to be executed inside the context of TPCDS 1TB. Now we can go ahead and create our external data source. The external data source tells SQL Server where the storage pool is and enables us to connect and query that data. However, we also need to tell SQL Server what format the data is in. In this case, the data is formatted in Parquet and is compressed using the Snappy codec. Now, I personally like to keep our database external tables separate from internal tables, and to do that, I use a schema. Now we can go on and create the external tables themselves, referencing the external data source and the file format that we just created. You'll notice that the top half of an external table is almost exactly the same as a regular table statement. The only difference is that we have this external keyword up here in the top, and also when you look down here in the with clause, you can see that we are pointing to the physical location of the data, as well as referencing that data source and file format that we just created. So we can go ahead and create that, and now do exactly the same for the item table. With that done, we can now just validate and virtualize those tables by querying them, and you can see that we can quickly get a result set back from each table, proving the connectivity is working just as we would expect. Now that the data has been virtualized, we can now actually use that data virtualization base to be able to perform data movement using T-SQL, in this case with the select into command. So now I'm just going to run that to move each table, the item and the date dimension, into SQL Server using select into. Now that the data has been moved into SQL Server, we can now simply run a validation of the row counts in SQL to show that the data has in fact moved. And you can see that the queries come back nice and quickly. Okay, now that we've done this, we can move over to our next notebook where we will look at how we can extend the data virtualization concept using Spark SQL. With this second notebook, we're going to build on our TPCDS data virtualization scenario and develop it further using Spark SQL. You can see that I've already created a Spark session and configured it for optimal use, as well as created a window to the Spark history server to be able to view performance. Now, in our data virtualization use case, we're going to focus on Q20 out of the TPCDS queries. Q20 is an interesting one because it is fundamentally like any canonical retail scenario. It has a catalog sales table, it has item, and it has date dimension. Remember, in the last notebook, we virtualized item and date dimension and moved them up to SQL. So now what we're going to do is use this notebook to use those SQL tables rather than the ones in HDFS. But in order to be able to kind of understand what we're doing, let's first baseline our query using all three tables in HDFS. And on the right hand side, we can keep an eye on the progress by looking at the jobs progress. And you can see here, because this is starting cold, we have the first iteration has an additional step to be able to list the leaf files and the directories, as well as initiate the job itself. Here you can see that the job has now completed and that the execution of the query took about 16 seconds. A second iteration will give us a warm run number, which should be less than that original measurement, and you can see that it is already looking good for that. And there you see 11 seconds. So with this baseline, let's move on and look at how we are going to virtualize the tables in SQL so that they're accessible by Spark. So the first thing that we need to do is to create a table in the Hive metastore that references our table in SQL. And we're also going to use the Spark Sql Connector that we open sourced as a team earlier this year. You can see here that we create the date dimension referencing the TPCDS 1 terabyte database in our environment. So we can now just run that query, and we can validate the end-to-end scenario just by running a simple select statement as before. With that done, we can repeat the same process, but now using the item table, but again, continuing to use the Spark Sql Connector. Awesome. Now, there are a couple of things to note about using creating tables in Hive Metastore, and we're just going to go through a little bit of that now, just to make sure that everybody understands what you need to be able to do to be able to achieve this result. Remember that the data is already on files in Parquet, in HDFS, in the storage pool. So what we're going to do here is just create another table definition in the Hive Metastore that points to that data set. You can see it looks and feels very much like a regular SQL table. The only difference here is we are also telling it to use Parquet as the data source, and we also tell Spark exactly where that data is residing. The other thing that we also include here is that this table is partitioned using the sold date SK as the partitioning a column. This is going to be important for performance when we think about things like partition pruning. However, because that table is itself partitioned, it doesn't automatically in Hive table format automatically assign all of those partitions to the metadata that we just created. So we actually have to run an additional command here just to be able to query the data and get the correct value. And so that query here is alter table recover partitions. That will take a little while to run. With the partitions recovered, we can now compute the statistics for our table. And for the columns on that table. We can now repeat that process for each of our smaller tables that we have created in SQL as well. So now we're ready to virtualize our query. You can see that now we're using all three external tables that we created in the Hive Metastore. Item and date dimension are coming from SQL. Catalog sales is the partition fact table running in HDFS. And that query has already completed. If we come over here onto the Spark side of the history server, we can see that that query actually ran in 9 seconds. So we are not actually paying a performance penalty here to actually query and bring the data in from SQL compared to actually having it available in HDFS. Now this is really important because it means that we can use the advantages of having a relational database engine like SQL Server to be able to do things like in-place update, and gives us a nice pattern for holding dimension tables and aggregates and things of that nature, which may require more fine-grained T-SQL style control over data, as well as having large additive fact tables that are partitioned and optimized for broader analytical queries running in HDFS, and leveraging the power that Spark provides through Spark SQL to be able to go and access that data and run those queries very, very efficiently. So that brings together both SQL and Spark SQL together in a single data virtualized scenario. I hope you enjoyed that. Well, that certainly was a different take on data virtualization in SQL Server 2019. What we were able to do there was show off all of the benefits of using SQL Server, such as being able to virtualize data and use data virtualization to move data using nothing but T-SQL, but we were also able to blend that with the capabilities of Spark SQL, virtualizing tables in SQL Server so that Spark could query large data sets in HDFS without any additional kind of performance penalty, which is a great scenario for modernizing and thinking about how you integrate relational technology into your data lake environments. So that's a unique capability that's available to you in BDC, and something that I hope that you're able to explore yourselves. Let's move on to the next demo. Now you may remember that when we launched BDC, we also launched with a performance white paper around Spark Scalability. This next demonstration is all about showing you the updates and the performance improvements that the Spark Scalability team have been able to achieve in the last year. And I think you'll find we've had some pretty exciting results. The original paper was co-authored with Intel, and we used the Databricks TPCDS 100 terabyte runtime in order to actually execute the TPCDS dataset. Now, at the beginning of the year, what we were able to show is linear scalability. We were able to show that across the vast majority of the queries, but we weren't able to show it across all of the queries. However, what we were able to show was that even at a 100 terabyte load, our open source Spark distribution was able to run the vast majority of all of the queries with linear scalability, which is a pretty good start for BDC. However, as I touched on, there were 10 queries that we weren't able to run, mainly because we ran out of memory even at 100 terabytes, even on a very large cluster. So we had to actually think about this and look into those queries. And this next section is really an exploration of what it is that we had to go and do in order to be able to enable the performance results that we have now achieved. So to highlight what was going wrong with the 10 queries, I've picked on one, Q37. Q37 is one of the smaller ones from a syntax perspective, but it still failed the query because we ran out of memory. So let's look at why. Well, we can see pretty quickly that there are only 4 tables involved, and of those 4 tables, only 2 are of any material size. One is inventory and the other is catalog sales. Now the inventory table is 2 billion records and the catalog sales table is 145 billion records. Now you can also see that there are some filters and also that the date dimension should see some pruning of partitions on the HDFS side. However, these tables are truly massive, and so what's happening here is we're seeing an out-of-memory exception because literally trying to pull too much data off disk and into Spark. So the solution for us here needs to mean that we need to be able to enable some form of disk spilling to be able to enable such large queries to run. So we went about and made a contribution to Spark, which we have made back to the community and back to open source Spark. And what we did was we actually optimized spilling. And we used the fact that actually here at SQL Server, we have some really, truly excellent engineers. And those engineers understand query performance and they understand query execution. And so what they did was they actually rewrote how performance spilling works so that we could get a much more scalable spilling result. Now what you can see here on this in this graph is that actually we have almost all of the queries executing within 5% of the total performance, which is a great improvement because now all of the queries are running, but only a handful of them, in fact, in this case 6, had any degradation in performance at all. And this is with performance spilling running for all the queries. And so we were able to now achieve 100% of all of the queries running, but we've also been able to make a contribution back to Spark to make sure that everybody gets this benefit. Now with BDC, we enable you to be able to do this using our Spark distribution, and we package that so you can deploy it as just part of a single BDC upgrade. So the advantage that you have with using BDC Spark is that whilst you're using open source Spark for compatibility and portability of workloads, you also get the convenience and the ease of use of a single deployment image with BDC managing the Spark environment for you. Now, as you can see, we've made more contributions to Spark than just the high performance sort merge join operator that you just seen in the previous slides. We've also made contributions to both the engine, the language, and JDBC utils in order to improve the overall Spark experience. And this is something that we are particularly committed to in the SQL Server team, and we've been doing so for quite a while now. That may be something that you're not particularly used to hearing about from SQL Server, but it is very much the reality of being part of Azure Data. Now, one other thing that we have also introduced this year, and we actually announced it at the Spark Summit, is a new Spark Sql Connector that is currently available and taking open source contributions from the community. I encourage you all to get involved and be part of the Spark community. That about wraps it up for our review of Spark at scale. You can see that the team have made some incredible improvements over the last year. Not only are we able to run at linear scale all the way up to 100 terabytes with Spark on Kubernetes, but we're also able to do so for all 140 PCDS queries. We've made performance improvements with the Spark sort join, merge join operator, and we've also introduced new connectivity to improve the experience between Spark and SQL. And for those of you curious about the size of our lab environment, we're using 16 nodes of kubeadm Kubernetes, each with 36 cores and 768 gig of RAM. To license that kind of environment for a production system would cost you about $120,000. But of course, if you're using BDC with Developer Edition, you can use it for free. Once upon a time, notebooks were the sole domain of the data scientist. However, they are extremely useful, and their adoption similarly has grown like wildfire with all of the different use cases that they've been able to support. It does kind of make you wonder how far you really can go using notebooks. One engineer at Microsoft seems to think that we haven't gone far enough, and that there is a long way to go in terms of how far we could really take this concept. This series of demos explores that as we look at going beyond the use cases of interactive query into troubleshooting, operationalization, and application development as a way of using notebooks to really drive next generation applications. Let's begin this exploration of notebook-driven development by seeing how notebooks can drive deployments. Here we're in Azure Data Studio, and what we're going to do is use the wizard to generate us a notebook that we can then use to deploy a new AKS cluster. To initiate the wizard, all we need to do is click on this new button here and hit Deploy a Server. This brings up the deployment options, and the one that we're interested in is SQL Server Big Data Cluster. I can accept the license terms and then choose my deployment target. In this case, AKS, although I could have chosen Azure Red Hat OpenShift or a kubeADM cluster if I wanted. Now, in order for this deployment wizard to work, it does require some tools to be installed on your client. If they're not there, the wizard will actually detect that itself and prompt you to install them, and will take care of that for you. But fortunately, I've already done that, so we can just hit Next on this occasion. This brings up the deployment configuration profile for BDC. And as you can see, there are two default configuration profiles provided, both through the AZ Data command line. So here you can see you can choose between HA and non-HA by selecting the radio button. And the difference you can see here in terms of the number of pods that are deployed. In the master pool, we will have contained AGs either on or off, and in HDFS and Spark, we'll have additional name node and Zookeeper instances in the HA configuration. You can also see that by default, storage and logs have also been defaulted, as well as your authentication and high availability experience. With that set, we can move over to the actual Azure settings for our AKS cluster. First things first, we can set what the name of the resource group is and the AKS cluster itself, as well as the number of nodes we wish to deploy and the VM size. Bear in mind that you will need to have a minimum number of nodes in order to be able to deploy your BDC, typically between 3 and 5. Now we come over to the Big Data Cluster settings themselves, and here you get to state a name for your BDC instance, the default administrator username and password. You can also pick whether you're using basic or AD authentication. Finally, if you expand the Docker settings, you can see the image tag and the image registry where we're pulling the images from. The image tag will tell you which version of BDC you're actually deploying. In this case, the latest version at the time of this recording, CU8. Now, in order to progress the wizard, I will need to put in a password. So I'll do that now and click Next. And this will bring us up to the scale settings for BDC. And here you can see how many pods for each pool we're going to be able to be deploying. In this case, I might choose to have more than 2 storage pool pods, so I can increase that number to 3. I can also choose the storage class for all of the instances, and if I wanted to use manage premium disk, for example, I could just update that here, as well as change the default size of the actual volumes that have been provisioned. Here, this summarizes the deployment and ends the wizard as far as the actual settings are concerned. And this is just a review and a summary of those, but you can see that everything that we have done has been propagated through to the summary page. From this point on, I can just click on Script Notebook to generate a new notebook that will have all of these settings in, ready for us to do our deployment. So let's do that now. Now that we have our generated notebook, we have everything we need to deploy both the AKS cluster and our BDC instance. All we need to do is to click Run All Cells and everything will be done for us. However, because this is an editable notebook, I could, if I wanted to, come in here and change any of the parameters that we used, as well as rerun commands to validate dependencies like kubectl versions. I can also see that I logged into Azure, created a resource group, and all of the information coming back from the creation of my AKS cluster. So what I'm creating here is something of a deployment artifact that I can then persist and use in perpetuity to be able to state exactly what happened at the point of that deployment. This could be useful for both successful deployments as well as failures, and that's going to be a recurring theme as we think about other scenarios in notebook-driven development. As we come down, you can see here that we both create our target profile, the deployment profile for BDC, and then we just pass that into BDC create when we come to actually create the BDC instance itself. You can see all of the information messages come up and that BDC has been created successfully. Lastly, we're just logging into the BDC cluster to capture and retain all of our endpoints here, and that's going to be the theme for the next notebook that we're going to be looking at, which is going to be around securing our endpoints with certificates. Lastly, all we need to do to actually register this BDC instance in ADS is to just click on this link at the end, and what that will do will generate us a link up here and connect us from ADS so that we can get on with the business of querying. Now, as I mentioned, one of the things that we want to be able to do is to secure our endpoints with certificates, and luckily we have a Jupyter book that we ship with BDC that you can just connect to by clicking F1 on the command palette and choosing it here. This creates and downloads the book, which we now need to save. We click save, we choose a location, and all we do is give it a name. And the book will be created here for us to be able to use. As you can see, Jupyter notebooks are organized much like regular books. They're broken down into chapters, and you can assign each chapter a given theme. In our case, the theme is BDC and all of the different management operations that you can perform with BDC using notebooks. The one that we're looking for right now is the certificate management chapter. So let's go and take a look and dig out CER 100, which is the one that we care about for this particular use case. CER 100 is a notebook that is designed to configure the cluster with self-signed certificates. It will generate a new root CA for the cluster and create new certificates for each of the endpoints of the cluster, specifically the HTTPS ones. It will then sign those certificates with the root CA and install that certificate into the BDC. Finally, it will then download the generated root CA into our client trust store so that we can make a secure connection to the client. Let's take a brief look through the notebook to see exactly what's going on. As you can see, this is a self-signed certificate that we're generating here at the top. When you come down into the notebook here, you can see that we're going to loop over a bunch of the other notebooks that are inside this chapter to perform specific functions. As we come down, you'll see we're generating some additional code and hiding and keeping that here to operationalize the notebook and make it more maintainable. But then we hit the main thing here, which is the iteration of the notebooks that we want to be able to run. And you can see that each notebook performs a specific function. Like, for example, this first one logs in AZ data into the controller. Notice that the output from executing this notebook is also persisted and stored on disk. And you can see that by just clicking on the notebook itself from the link inside our original notebook. As we scroll down, you can see that this happens on several occasions, each notebook performing a specific function in the process of rotating those certificates for us. And at the end, there is a final validation where we check to see whether or not the cluster is still healthy using another notebook. And when complete, we get the notification at the end. Now that CR100 has run successfully, let's prove it by logging into the Grafana dashboard. First thing we need to do is to grab the endpoint, and we'll do that by making a connection to the controller. and then iterating, asking it for the endpoints that we need. One of the nice features about BDC and AZ Data is that it does give you these nice usable features for connecting and formatting the results. So we can take here our Grafana link, open up our instance, pass in our username and password on the secured endpoint, and know that we're there. Notice the endpoint has been secured. So far in our journey through notebook-driven development, we've explored the standardization of deployment and management tasks. Now we're going to look at application development and operationalization, specifically scheduling notebook applications. The notebook application in front of you is a very simple application, but it does something quite clever. What it is actually doing is it is searching inside the storage pool of BDC for a specific location and counting the number of text files that it can find in that specific location. However, the location it is specifically looking for is where we will actually be saving execution instances of this particular notebook. So essentially, it's counting itself. Now, what we're going to do next is schedule it. And to that, we need to use the Operationalization chapter and specifically OPR 100. So let's go and grab that notebook. OPR 100 provides us with a mechanism to both containerize a notebook and also to schedule it. Here we can see through the parameterization section at the top of the notebook, it gives us the ability to pass in an application name and a version of the application and a schedule. Underneath here, we can see the notebooks that we wish to deploy. In our case, the notebook-driven development notebook. Above it, we have a dependency. This is a AZ Data login notebook so that we can actually save the results back into the query so that we can count them later on. You can see that this notebook does a lot more than just create the container though. It also creates a dashboard for us to be able to monitor the progress of all our applications and help set up some core infrastructure so that we can actually monitor all of the progress of this application. So let's run this now and take a look at the dashboard when it's ready. Okay, so you can see we now have installed a brand new dashboard into Grafana. And there you can see the first iteration of our new application has now executed. This dashboard is getting its data from a SQL Server database that was deployed by the OPR 100 notebook. And you can see that by clicking on the data sources. There's an additional SQL Server data source that has been configured. Let's quickly go and review that and look at the HDFS storage now. So if we go back into Azure Data Studio, refresh our databases, you can see that there is this new database called Runner. And if we click into this and select, say, the data out of the table metrics table, we will be able to see all of the iterations of that notebook that has now executed. Furthermore, if we come down into HDFS, we can break into the HDFS object, see our app deploy. Here is our application, and by drilling in, we can see all of the iterations of that execution of that notebook that has occurred since we set that job in motion. Finally, I just want to show you how you can use AZ Data to enumerate all of the notebook applications that you have deployed. So if we come in here and type AZ Data app list, we'll see that all of our applications have been deployed and they all are exposed on a RESTful endpoint so that we can interact with them as well. Okay, now let's see how far we can really stretch this by looking at a more complex application, and for that we're going to need the canaries. So it's back to the Jupyter book and to a new chapter that we hope to bring to you soon, which is called the canaries. This is an early warning system and a sample application that you can use to preemptively monitor your BDC environment. As you can see from the list of the canaries that we deploy, these applications actually exhaust every touch point within the BDC and are looking to check for the health of the cluster itself. And we use this even in our own test environments. So we're looking forward to sharing this with you soon. Now, I'm just going to execute this, and it will take a little while to run, but it will show you the art of the possible once we have all of these canaries up and running in a BDC. So let's just hit go, and I'll be back with you shortly. With the notebook complete, you can now see all of the canaries that we have. One for HDFS, one for Spark, one for the notebook application pool, one for our health monitors, and SQL master pool as well. It's even looking for crash dumps and other things like free disk space checks as well. So let's go and see what it looks like in Grafana. And here is a new dashboard that is looking across all of the canaries, so you can see how they are interacting with the cluster and checking all of the health across the nodes and all of these different tests that are running on varying schedules using the notebook operationalization that I showed you with the sample application. Well, that's quite a comprehensive overview of everything that you can do in notebook-driven development. We've looked at deployment, management, standardization, application development, and operationalization of notebooks. I hope you've enjoyed it, and I look forward to bringing to you the Canary application soon so that you can explore this in detail more yourself. We really only have scratched the surface of what's possible here, and I look forward to seeing what you can do with your notebook applications and BDC. Well, I hope you agree that BDC really does have some quite interesting capabilities. Now, you might not have thought about them in that context before, or you might not have even been aware that BDC was capable of those things. But as you have seen, we are able to do some really quite imaginative things with BDC once you open your mind to the capabilities. We've spoken about contained availability groups and looked and had a quick sneak peek at our new configuration management experience. We expanded the scenario of data virtualization and started to look at how you could use Spark in that scenario as well, not only for running large queries, but also integrating with SQL to separate out your dimensions and your facts, leveraging the power of SQL, doing what it does best, and also using Spark for what it can bring to the party. We also looked at Spark at scale and looked at how we have developed the Spark engine in the last year to enable us to be able to run truly massive workloads with Spark engine. And then lastly, we looked at notebook-driven development and what an interesting scenario that is. How you can take something that's as simple as a notebook and operationalize it, schedule it, and run it as a complex notebook application. Thank you for spending the last hour with me. I've really enjoyed it, and I hope that you are able to enjoy the rest of your past summit as well. Please do share your feedback with us. I hope you've enjoyed the session, but I do always appreciate your constructive feedback, both good and bad. And don't forget, BDC is a learning pathway for the past summit, and there are some truly great sessions and some great speakers who have put in a lot of time and energy to provide you with some first-class educational content, and I really do encourage you to make the most of that. Thank you all for joining, and I just want to say thank you very much to my peers in the engineering team and in the PM team for making the last year so much fun. Have a good day, everybody. Bye for now.